In ancient Greece, the treatment of disease was based more on philosophy than in genuine understanding of human anatomy. Surgical procedures were rare, and human dissection was not an accepted practice. As a result, physicians had little first-hand information about the inside of the human body. It wasn't until the Renaissance that the science of human anatomy was born. A Belgian physician, Andreas Vesalius, shocked many by deciding to investigate anatomy by dissecting human bodies. Bodies that he was often forced to procure under cover of night.
For medical students like Vesalius who wanted to dissect, they had to just find bodies from outside of the legal channels. Once Vesalius became a professor at Padua, the person in charge of executions was actually a friend of his, so Vesalius could even go in and observe the living prisoners who were waiting execution and say, I want that one, and then the person would be executed.
According to Dr. Bilabil, Vesalius was determined to pass on the first-hand knowledge that he had gained from his skillful dissections by writing a book on human anatomy. The result was his De Humani Corporis Fabrica, on the structure of the human body. First published in 1538, Fabrica is considered one of the greatest books in medical literature. It's regarded as one of the greatest discoveries in medicine because it contains the first accurate description of the interior of the human body.
This was the first major challenge to the authority of the ancient Greek physicians. The book had a great sale that must have been to a wealthy, literate public that went far beyond the medical profession. And the pictures are very elaborately keyed in with the written text, so it just made knowledge of human anatomy much more accessible.
Thanks to Vesalius, the study of human anatomy through dissection became an essential component of medical training and helped lead to our next great discovery. The human heart, a muscle the size of a fist, beating more than 100,000 times a day, over 2 billion heartbeats by the time you turn 70, pumping more than 5 gallons of blood a minute. Blood flows through the body, traveling a complex highway of arteries and veins. It's estimated that if all the blood vessels in just one human body were placed in a line, they'd reach some 60,000 miles, more than twice around the Earth. But in the early part of the 17th century, how blood works in the body was misunderstood. The prevailing theory was that it ebbed and flowed through the heart by way of pores in the soft tissue. Among those who believed in this theory was an English physician named William Harvey. He was fascinated with the workings of the heart. The more he studied the beating hearts of animals on his dissecting table, the more he realized the accepted theory of blood flow couldn't be right.
Quite explicitly says, I began to think whether the blood might have a motion, as it were, in a circle. And then he begins a new paragraph and he says, and this I afterward found to be true.
In his dissections, Harvey observed that the heart had one-way valves that kept the blood flowing in one direction. Some valves let the blood in, while others let it out. Here was his great discovery. The heart, he realized, was pumping blood into the arteries, where it then circulated through the veins, coming full circle back into the heart, ready to start the cycle all over again. Today, it's obvious that blood circulates in the human body. But in the 17th century, William Harvey's discovery was revolutionary.
This was really striking at the very core of traditional medical ideas. And at the end of his treatise, Harvey says, when I think of the countless implications that this will have for medicine, I see a field of almost unlimited possibilities.
Harvey's discovery led to major advances in anatomical research and surgery, and simple, life-saving ones, too. In operating rooms and trauma centers around the world, surgical clamps are used to stem the flow of blood and keep a patient's circulation intact. A simple device, but each one a reminder of William Harvey's great discovery. Another great discovery having to do with blood occurred in Vienna in 1900.
There was a great enthusiasm throughout Europe for transfusing blood. And at first there were claims that this had marvelous therapeutic effects, but this was followed within months by reports of people who died.
Why did some blood transfusions work and others didn't? An Austrian physician named Karl Landsteiner was determined to find the answer. He mixed blood samples from various individuals and studied the effects. In some cases, the samples mixed safely. But in other combinations, the blood clumped and became sticky. On closer examination, Landsteiner found that clumping occurred when certain proteins called antibodies in the recipient's blood bonded to other proteins called antigens on the donor's red blood cells. For Landsteiner, this was the moment of discovery. He realized that not all human blood was the same. He determined that human blood could be divided into 4 distinct groups. He called these blood groups A, B, AB, and O. He realized that blood transfusion could only be carried out safely when people received blood from someone who shared the same blood group. The impact of Landsteiner's discovery was immediate. Within a few years, blood transfusions were being practiced around the world, saving countless lives. By the 1950s, accurate blood typing helped make organ transplants possible. Today, in the United States alone, blood transfusions are performed about once every 3 seconds. Without them, it's estimated that 4.5 million Americans would die each year. While the first great discoveries about human anatomy enabled physicians to save more lives, there was little they could do to reduce pain. Without anesthesia, surgery was a waking nightmare. Patients were held down or lashed to a table. Surgeons worked as quickly as possible. The sooner the torment was over, the better. In 1811, one woman wrote of the ordeal.
When the dreadful steel was plunged in, cutting through veins, arteries, flesh, nerves, I needed no injunction not to restrain my cries. I began a scream that lasted during the whole time. So excruciating was the agony.
Surgery was a last resort. Many people simply chose to die rather than to have the surgeon cut into them with his knife.
According to Dr. Harden, for centuries, various remedies were used to help ease pain during surgery. Some, like opium or an extract from the mandrake root, were narcotics. By the 1840s, several individuals were on the trail of finding a more effective anesthetic. In Boston, 2 dentists, Horace Wells and William Morton, both of whom knew each other. And in Georgia, a small-town doctor named Crawford Long. They experimented with 2 chemicals thought to have the potential for reducing pain: nitrous oxide, or laughing gas, and ether, a liquid mix of alcohol and sulfuric acid. Just who discovered anesthesia is still a matter of debate. All 3 doctors claimed it. One of the first public demonstrations of anesthesia occurred on October 16, 1846. William Morton had been experimenting with ether for months, trying to find a dosage that would enable a patient to undergo surgery pain-free. With a special device of his own creation, he convened a demonstration before an audience of Boston surgeons and medical students. He administered ether to a patient who was about to have a tumor removed from his neck. Morton waited. The surgeon made the first incision. Remarkably, the patient did not cry out. After the surgery, the patient reported feeling nothing throughout the entire operation, and word quickly spread. Surgical pain was conquered. Anesthesia had been discovered. Despite the discovery, many people were reluctant to use anesthesia. Some religions believed that pain was to be tolerated, not relieved, especially during childbirth.
Queen Victoria played a role in this. In 1853, she was giving birth to Prince Leopold, and she asked for and was given chloroform, and found that it relieved the pain of childbirth. And shortly thereafter, women in general said, I think I'll have chloroform too. If it's good enough for the Queen, it's good enough for me.
It's also impossible to imagine life without our next great discovery. Imagine surgery without first being able to see where to make the incision, which bone may be broken, where the bullet may be lodged, or what pathological condition may exist. The ability to see inside the human body without cutting it open was a turning point in the history of medicine. To find out more about it, I paid a visit to Betty Ann Holtzman-Kevles, a professor of history at Yale University.
At the end of the 19th century, people were using electricity, but they didn't understand what it was. This is a tube, which I believe is a copy of the one made by the Siemens company, which was the one that would have been used by Röntgen.
Röntgen was German physicist Wilhelm Röntgen. In 1895, he was experimenting with a cathode ray tube, an evacuated glass cylinder, a vacuum tube. Röntgen marveled at the glow created by the rays coming from the tube. For one of his experiments, Röntgen enclosed the tube in black cardboard and darkened the room. Then he turned on the tube. Moments later, something startled him. A photographic plate in his lab was glowing.
So he realized that something very unusual was going on, and he knew that whatever the ray that was coming out of here was not a cathode ray. He also discovered that it didn't respond to magnetism. You couldn't deflect it the way you could cathode rays. It was something altogether new, and he called it X for unknown.
Like in algebra.
Absolutely.
Röntgen had accidentally discovered a radiation unknown to science, which he called X-rays.
After having been rather mysterious for several weeks, he called his wife down. He said, Bertha, let me show you what I'm doing, because no one's going to believe this. And he had her put her hand under the ray, and he took an image of her hand. Well, the image was a lot like this picture. And she is reputed to have said, I have seen my own death. Because in those days, you only saw a skeleton after someone had died. The idea of seeing part of the body on an image of a living person was just beyond anybody's imagination.
Yeah. It was as if a secret door had been opened, revealing a hidden universe. Röntgen had discovered a powerful new technology, one that led to a revolution in medical diagnostics.
In the history of science, the discovery of X-rays is the only discovery that was made when no one was looking for it. It was totally by chance, but as important, once it was discovered, it was accepted by everyone in the world. There was no controversy. Within a week or two, our world had changed.
Today, the legacy of Röntgen's discovery can be found in the powerful technologies that followed in its wake, from the CAT scan that helps diagnose what ails us, to NASA's Chandra X-ray telescope, which astronomers are using to detect X-rays from the furthest reaches of space. All from a discovery that happened by accident. Some discoveries, like X-rays, seem to come out of the blue, while others, like our next great discovery, develop over time, with one scientist contributing to the work of another. Vienna, 1846. A city of beauty and culture. But at Vienna General Hospital, there was the specter of death. Many of the women who came here to give birth were dying. The cause? Childbed fever, an infection of the uterus. When Dr. Ignaz Semmelweis came to work at the hospital, he was alarmed at the scope of the problem and intrigued by a curious discrepancy.
They had two wards. In one, the mothers were delivered by physicians. And in the other, the mothers had their babies delivered by midwives. Semmelweis noted that in the ward where the physicians delivered babies, 7% of the mothers died from what was called childbed fever. In the ward where the midwives delivered, only 2% of the mothers died from childbed fever. And this bothered him because physicians have more training. They're supposed to do better by their patients.
Semmelweis was determined to find out what was going on.
He noted that one of the main things that physicians did that midwives did not do was to conduct autopsies on these mothers after they died. Then they would go back and deliver babies or examine mothers without washing their hands, just like an auto mechanic who would finish up on one car and then move to the next car without washing his hands to get the grease off. He didn't see any reason to have to do this.
Semmelweis wondered if the doctors were carrying some invisible matter on their hands, which they passed on to their maternity patients, causing them to die. To find out, he conducted a test.
He decided that he would have the student physicians under his control wash their hands in a chlorine solution. And suddenly, the percentage of maternal deaths dropped to 1%. That's lower than the midwives.
With this demonstration, Semmelweis realized that infectious disease, in this case childbed fever, has a single cause. If you eliminate the source of the infection, the disease does not occur. But in 1846, no one had made the connection between bacteria and infections. As a result, Semmelweis's idea was ignored. It would take 10 more years before another scientist would turn his attention to germs. His name? Louis Pasteur. Pasteur had lost 3 of his 5 children to typhoid fever, which perhaps explains why he was determined to find the cause of infectious diseases. It was Pasteur's work on behalf of the beer and wine industry that put him on the right track. Pasteur was trying to find out what was spoiling so much of the country's wine production. He discovered that the spoiled wine was contaminated by microorganisms, germs, and the germs were causing the wine to sour. But with a simple heat treatment, he showed that the germs could be killed off and the wine saved. The pasteurization process was born. So when it came to finding the cause of infections and contagious disease, Pasteur knew where to look. Germs, he said, cause specific diseases, and he proved it through a series of experiments and demonstrations that led to his great discovery, germ theory.
The germ theory literally marks the beginning of modern medicine. The germ theory has one central idea, that one microorganism causes one disease in everybody.
Our next great discovery happened in the 18th century, when smallpox killed an estimated 40 million people around the world. Doctors were unable to find the cause or discover a cure. But in a small English village, talk of how some locals were immune to smallpox got the attention of a country doctor named Edward Jenner. It was said that villagers who worked in the dairy business were safe from smallpox because they'd already been infected by cowpox, a related but less severe disease that afflicted cattle. Cowpox victims suffered fever and sores on their hands, but little else. Jenner studied the phenomenon and began to wonder if the pus in the cowpox sores was somehow responsible for protecting against smallpox. On May 14, 1796, during an outbreak of smallpox, he decided to test his theory. Jenner withdrew pus from the cowpox sores on the hands of a dairymaid. Then he visited another family in the village. He inoculated a healthy 8-year-old boy with the cowpox virus, confident in the outcome. In the days that followed, the boy developed a slight fever and some cowpox blisters, then recovered. 6 weeks later, Jenner returned. This time, he inoculated the boy with smallpox, then waited. The moment of success or failure was at hand. Within days, Jenner had his answer. The boy was completely healthy, resistant to smallpox.
Vaccination for smallpox was revolutionary because it represented people's attempt to intervene into the disease process, to prevent it up front. This is the first time a man-made product had been used actively to prevent disease before it occurred.
50 years after Jenner's discovery, Louis Pasteur pushed the concept of vaccination even further, developing vaccines against rabies in humans and anthrax in sheep. And in the 20th century, Jonas Salk and Albert Sabin independently developed vaccines against polio. And we owe it all to Jenner's great discovery. Our next great discovery depended on the contributions of researchers working independently on the same problem over many years. Throughout history, scurvy was a painful disease that inflicted sailors with hemorrhaging and skin lesions. Finally, in 1747, a Scottish naval surgeon named James Lind found a remedy. He discovered that scurvy could be prevented by including citrus fruits in a sailor's diet. Another disease afflicting sailors was beriberi, a degenerative disease that attacks the nerves, heart, and digestive system. Toward the end of the 19th century, a Dutch physician named Christian Eijkman traced its cause to diets that included polished white rice rather than unpolished brown rice. While both these discoveries indicated a link between diseases and dietary deficiencies, it wasn't until the work of British biochemist Frederick Gowland Hopkins that the connection became clear. Hopkins suspected that our bodies need certain nutrients that can only be acquired by eating certain foods. To prove his point, he conducted a series of experiments. He fed mice a synthetic diet consisting entirely of pure protein, fats, carbohydrates, and salts. The mice became sick and stopped growing. But given a small amount of milk, the mice recovered. Hopkins had discovered what he called accessory food factors, which later came to be known as vitamins. Beriberi, it turned out, was caused by a deficiency in thiamine, vitamin B1, which was lost in polished rice but plentiful in the natural grain. And citrus prevented scurvy because it contained ascorbic acid, vitamin C. Hopkins' discovery was a major shift in our understanding of the importance of nutrition. Vitamins are responsible for so many of our body's normal functions, everything from fighting infection to regulating metabolism. It's hard to imagine life without them, just like our next great discovery. World War I, more than 10 million dead, many from the infection of their wounds. After the war, research intensified to find safe methods of repelling the bacterial invaders. Among those on the case was Scottish physician Alexander Fleming. While studying Staphylococcus bacteria, Fleming noticed something unusual growing in the culture dish, a mold, Penicillium notatum. He saw that the bacteria surrounding the mold had died off, which led him to speculate the mold was producing a substance that was lethal to the bacteria. He named the substance penicillin. For the next several years, Fleming tried extracting penicillin and applying it to treat infections. But he was unsuccessful and eventually gave up. Fleming's work, however, proved invaluable. In 1935, scientists Howard Florey and Ernst Chain at Oxford University came across a record of Fleming's curious but incomplete work with penicillin and decided to investigate. This time they successfully extracted and purified penicillin. And in 1940, they tested it. They injected 8 mice with lethal doses of the bacteria Streptococci. Then they injected 4 of the mice with penicillin. Within hours, they beheld the results. The 4 mice not treated with penicillin were dead, but 3 of the 4 that had been given penicillin were alive. From Fleming to Florey and Chain, the world's first antibiotic was born.
It was a miracle drug. It cured so many diseases that had caused so much pain and suffering. Strep throat, rheumatic fever, scarlet fever, syphilis, and gonorrhea. It was things that we wouldn't even think about today should kill you.
Our next great discovery came to the rescue in World War II. It provided soldiers with a drug to fight dysentery while they fought in the South Pacific. Eventually, it also led to a revolution in the chemotherapeutic treatment of bacterial infection. The scientist who made it all happen was pathologist Gerhard Domach. In 1932, Domach was studying the potential medical applications of some new chemical dyes. Working with a newly synthesized chemical dye called Prontosil, Domach injected it into some lab mice that were infected with Streptococci bacteria. The dye attached to the bacteria just as Domach had hoped, but the bacteria survived. The dye, it seemed, wasn't toxic enough. Then something startling happened. While the dye didn't kill the bacteria, it did inhibit their growth. The spread of the infection was stopped. The mice recovered. It's not clear when Domach first used Prontosil on a human patient, but the new drug achieved fame when it saved the life of a boy seriously infected with Streptococci. The patient's name? Franklin D. Roosevelt Jr., son of the President of the United States. From that moment on, Domach's discovery was a sensation. Because Prontosil contained what was known as a sulfanilamide molecular structure, it was called a sulfa drug, the first of its kind. A synthetic chemical substance that could cure and prevent bacterial infection. Domach had opened the door to a revolutionary new approach in the treatment of disease, the use of chemotherapeutic drugs, a discovery that would go on to save tens of thousands of lives. Our next great discovery helped save the lives of millions worldwide who were afflicted with diabetes. Diabetes is a disease that disrupts the body's mechanism for processing sugar, which can lead to blindness, kidney failure, heart disease, even death. For centuries, physicians studied diabetes, searching in vain for a cure. Finally, in the late 1800s, a breakthrough occurred. It was discovered that the bodies of diabetics had something in common. A group of cells in the pancreas was always damaged. These cells produced a hormone that controlled blood sugar. That hormone was called insulin. Then, in 1920, another breakthrough. Canadian surgeon Frederick Banting and a graduate student named Charles Best were studying how insulin was produced in the pancreases of dogs. On a hunch, Banting took an extract from the insulin-producing cells of healthy dogs and injected the extract into other dogs already afflicted with diabetes. The results were astounding. Within a few hours, the blood sugar levels of the diabetic dogs decreased significantly. Now Banting and his team set their sights on finding an animal whose insulin bore a close resemblance to human insulin. They found a close match in the insulin taken from cow fetuses, purified it for safe treatment, then in January 1922 conducted the first clinical trial. Banting administered the insulin to a 14-year-old boy dying of diabetes. And the boy made a dramatic recovery. How important was Banting's discovery? Why not ask the estimated 13 million Americans who rely on insulin to control their diabetes every day? Cancer, the second leading cause of death in the United States. Intensive research into its origins and development has spawned remarkable scientific breakthroughs, perhaps none more significant than our next great discovery. To find out about the discovery, I caught up with two Nobel Prize-winning cancer researchers, Michael Bishop and Harold Varmus, at the Memorial Sloan Kettering Cancer Center in New York City. Varmus and Bishop first joined forces to research cancer in the 1970s. At the time, there were several prevailing theories about the cause of the disease.
The malignant cell is complicated. It's not just a cell that can replicate indefinitely. It's a cell that can invade, elicit new blood vessels. It has a very complex capability.
One theory concerned the Rouse sarcoma virus, a virus that caused cancer in chickens. When the virus attacked the cells of a chicken, it inserted its genetic material into the host's DNA. According to the theory, the viral DNA later became a cancer-causing agent. A second theory suggested that once the Rouse sarcoma virus inserted its genetic material into the host cell, the cancer-causing genes didn't activate themselves, but remained dormant until triggered by outside influences, such as harmful chemicals, radiation, or even viral infections. These cancer-causing genes, called oncogenes, became the focus of Varmus and Bishop's research.
The fundamental question was, does a human cell, does the human genome contain genes that either are or are capable of becoming oncogenes of the sort that are in a virus?
Tumor-causing genes.
Tumor-causing genes, cancer-causing genes, right. Are they in there or not?
So what did you discover?
First, we started with the chicken because that's where this virus came from. Is there a gene in chickens? And then later, is there a gene in other birds, in mammals, in humans, related to the cancer gene of the Rouse sarcoma virus?
So what we did was to make a radioactive molecule that could be used as a probe for asking whether the oncogene of Rouse sarcoma virus resembled a normal gene present in the chromosomes of a chicken.
And the answer was yes.
It was a landmark discovery. Varmus and Bishop found that the cancer-causing gene was already present in the DNA of normal, uninfected chicken cells. Even more remarkable, they found it in human DNA as well. Proof that the seeds of cancer may already be inside each of us at the cellular level, just waiting to be activated. How can one of our own genes, which we've had all our lives, cause cancer?
When cells divide, mistakes are made. They are more frequent if the cell is stressed by
Cosmic ray.
Cigarette smoke.
Cigarette smoke is a good example. It is important also to recognize that when cells divide, they have to copy 3 billion base pairs of DNA. And anybody who's ever tried to type something knows that it's not easy to do that. We have spell check mechanisms that allow detection of mistakes and repair of those mistakes, but still, things slip through when you're doing things on such a large scale.
So why is this a great discovery?
That difference between the gene in the virus and the gene in the cell exemplifies the fundamental way people were trying to think about cancer, and we now do think about cancer, that small changes in particular genes in our cells can convert cells from controlled regular growth and other behavior to the behavior of a malignant cell. And this really was the first direct illustration of that sort of thing.
Is modern cancer research a result of your discovery?
It's a fundamental platform on which almost all molecular approaches to cancer is built. And indeed, you know, as someone now who runs a cancer hospital, what's exciting for me at the moment is seeing how understanding of cancer at the molecular and genetic level is influencing the way in which we treat a lot of our patients.
Why is it important? Looking for this kind of gene is vital in diagnostics now. It's vital in prediction of how cancers are going to behave. And above all else, it's vital because it's provided these targets for truly specific therapy that we simply didn't have before.
The city of Chicago, population about 3 million. The same number of people who are dying each year from AIDS, one of the worst epidemics in modern history. The first clues about the disease emerged in the early 1980s. Researchers in the United States reported that a rising number of patients were dying from rare infections and cancers. Blood samples revealed that the patients had extremely low levels of CD4 T lymphocytes, white blood cells vital to the body's immune system. In 1982, the Centers for Disease Control and Prevention gave the disease a name: AIDS, Acquired Immune Deficiency Syndrome. 2 researchers took up the case: Luc Montagnier at the Institut Pasteur in Paris and Robert Gallo at the National Cancer Institute outside Washington, D.C. Both share credit for the breakthrough discovery that eventually uncovered the cause of AIDS: HIV, human immunodeficiency virus. What is different about human immunodeficiency virus from another virus, like the flu or something?
Firstly, the virus doesn't give evidence of disease for years. Let's take an average, 7 years.
7 years.
Second problem that was rather unique. By the time a person presented themselves with AIDS and said, you know, I'm sick, I'm going to go in the hospital, they had a myriad of other infections. What was the cause? How do you demonstrate which one of these is the cause of the disease?
In most cases, a virus exists for one purpose: to infect a host cell and reproduce. Typically, it attaches itself to the host, then releases its genetic information into the cell. This enables the virus to take over the cell's normal functions, redirecting them to produce new virus particles. These particles are then released to attack more cells.
HIV is not a conventional virus. It belongs to the family of viruses, or the category of viruses, that scientists call retroviruses.
How are retroviruses different?
Just like the virus classes that include polio, or virus classes that include influenza, retroviruses are another type of virus. What's unique about a retrovirus is that, and what we might say is the sine qua non of a definition of a retrovirus, is its genetic information in the form of RNA is converted into DNA. But it's what happens to DNA that gives us our problem.
And what is that?
The DNA gets incorporated into our genes. The DNA of the virus becomes part of us.
As the T helper cells reproduce, they're reproducing with the virus, the retrovirus DNA in them.
Exactly.
Forever. You never get over it.
You'll have cells harboring the genetic information for the virus, sometimes making virus, others silent, quiet, perhaps hidden, but only later to pop out and reproduce virus again. That means very rapidly, upon infection, we're establishing an infection that's likely to be lifelong. That's the crux of the issue for me.
A cure for HIV remains elusive, but the discovery that HIV is a retrovirus and that HIV causes AIDS has led to breakthroughs in the fight against the disease and beyond. What has changed in medicine since the discovery of retroviruses, or more specifically, the discovery of this virus?
AIDS has been the lead ship in showing that antiviral drug therapy is possible. In general, it was thought, because viruses usurp the cell, our cells, for how they reproduce themselves, it would be nearly impossible to target them effectively without poisoning a person badly.
You're saying that nobody was investing in, if I may, antivirotics?
AIDS has opened the door to antiviral research in the pharmaceutical companies and in universities broadly across the world. AIDS has also had positive spin-offs sociologically. I witnessed firsthand a difference between developing and developed nations. You can't just drop the drugs on the beach and run home. It requires training on how to use the drugs, and we have that relationship with several African countries now.
So this is an irony, that this horrible disease is actually bringing people together.
I think so.
Thanks to the discoveries that we've just seen, the world has changed. From germ theory to uncovering the origins of cancer, these breakthroughs have altered the course of history, saving countless lives and pushing the boundaries of our medical knowledge to where we are today, ready for the next breakthrough, the next great discovery.